So this is section 10.3, which is chi-squared goodness of fit test. Okay, so we're going to do a little introduction into it to look at the reasoning behind it. So for example, suppose that we know that the market shares for 4 microwave oven brands in our city are 20%, 35%, 30%, and 15%. We want to expand our store to a new city. We need to know how many microwaves of each brand to stock. We assume that the market shares will be the same as our city. To test this, we take a sample of 400 customers in the new city to see which brand they will buy. So in the new city, we have these observed counts. So brand 1 was 102, up to brand 4, which was 57. Okay. So how are we going to decide if the new city has the same distribution of market shares as our old city? Okay. So there are some ideas, not necessarily only one idea, but what would you try and look at to see if your market shares are the same?
We'll have the percent we match to the old.
So compare the old and new percents. What other ideas do you guys have? We can compare the percentages, which also means proportions, or we can compare when we worked with proportions before, what did we change it to before we found probabilities for proportions? Counts. So if you would compare the old and new percentages or counts, either way. Okay, so I'm using the notation, so we're going to call P1 be the true proportion and new city customers prefer brand 1, up to P4 will be the true proportion and new city customers who prefer brand 4. So our null hypothesis here, status quo, would be that they have the same distribution as last time. Okay. Actually, let's go back up and let's just introduce a little bit of notation. Okay. So this, right here, this is our proposed distribution. So for our new city, we propose that this might be the distribution that fits it. Okay? And so we're asking the question, is the proposed distribution a good fit for our data in the new city? So just introduce a little notation, that's the proposed distribution. And then when we went to the new city and actually went out and asked them what they're going to buy, this is our actual data. Right. So now we look at our hypotheses. Again, the status quo would be that the proportions are the same as in our old city, which means that the proportion for new customers in the new city who prefer brand 1 would be equal to what?
Brand 1's percent.
Okay. So for our old city, brand 1's percent was 20%. So, our null hypothesis is that the proportion in my new city will also be equal to 20%, or, since we're doing proportions, 0.20. And if it's the same as in our old city, the true proportion of the new city for brand 2 should be the same as the old city, which was 35%, or 0.35. And the proportion of like brand 3 should be the same as the old city, so 0.30. And the proportion of like brand 4 should be 0.15. So then that's the status quo, but these are my proportions. What would be the opposite of that, or what makes that statement not true?
At least one is not equal.
Yes, well, it's not that they're all wrong, but at least one of those proportions is wrong. So at least one of our proposed proportions is wrong. So just like the NOVA test, we don't know how many are wrong or which ones are wrong, but at least one of those proposed proportions is incorrect. So our null hypothesis could be that. There's also another way that we could write our null hypothesis, just depending on how the problem is given to us, which might make more sense. Okay. You could just say the null hypothesis is that the proposed distribution fits our data. Hence why it is called the chi-square test goodness of fit. So our whole idea behind this is the proposed distribution a good fit for our data? Okay. Now that implies that my proportions are the 0.2, 0.35, 0.3, and 0.15 because that is our proposed distribution. And the alternative to that would just be that the proposed distribution does not fit our data. Now let me ask you, if the proportion of customers who prefer brand 1 is 20% and we have a sample of 400 customers, okay, how many would you expect to prefer brand 1 and how would you figure that out? So we expected for brand 1 is 400 times 0.2, which gives me 80. Okay, and realize that should be fairly instinctively. Okay, so if your proportion is supposed to be 0.2, you have 400. 400 times 0.2 gives you the expected count of 80. So we can come down here for all of the 4 brands and find the expected count for each one. So for brand 1 was 80. For brand 2, we're going to do 0.35 times 400, which gives me 140. And 30% times 400 gives me 120. And 0.15 times 400 gives me 60. So those are all of our expected counts, and then for our observed counts, we just scroll up and see, okay, they told us what my observed counts were. So my observed counts were 102, 121, 120, and 57. So so we said before that we wanted to either compare the old and new proportions or percentages, or we could also compare the counts. The reason we want to compare the counts is because someone went through and found a nice test that works with comparing the counts. Okay, so we want to compare expected counts to observed counts. Now, looking at these numbers, how do you feel about whether or not we were correct? Just kind of going gut instinct.
First two are off.
Yeah, the second two seem to be pretty close, but the first two seem to be maybe off. Okay, and of course our question is always, are the differences just due to which sample I picked, or do we really have different population proportions than we were suspecting? So to do that, we want an actual test statistic so we can see how big that difference truly is. Now, if you look in your book, there are two different test statistics. Okay? Really, they're equivalent. One just uses natural logs to try and make your computations a little bit easier. Okay? But we're just going to use the Pearson chi-square test statistic because it's the more common one that you would see later in practice. And it's chi-squared equals. So what you're going to do is add up all cells for each cell. You do observed counts minus expected counts, squared divided by expected counts. And it will be a chi-squared distribution with k minus 1 degrees of freedom. Now, if our observed counts and expected counts are really different, what kind of numbers would you be expecting? Big numbers. So if the alternative hypothesis is true, so those observed counts and expected counts were really different, that would mean that our proposed probabilities were wrong. And so our alternative hypothesis is true, we'd be looking for big values of our chi-square test statistic, which means that our test will always be a right tail. So no matter what problem it is, for this test, we will always be looking for the p-value in the right tail. Okay. Why do you think we bother dividing by this expected counts? Okay, subtracting the observed and the expected makes sense. Squaring it makes sense, so you don't just have the positives and negatives cancel each other out. Why do we have to divide by expected counts?
Just to normalize it, 3.0 and 1.
Okay. It would do that. Put it between 0 and 1. What were you going to say?
The proportion.
Okay. I was just thinking of it as like a scale. Okay. So if you're 3 off, but all of your counts are between like 1 and 5, that seems like a pretty big difference. But if you're 3 off and your counts are around like 800, do you really care about a difference of 3? Okay. No, so it's just kind of put it on a scale of, is this difference really important based on how big my counts are? So here's our information for the chi-square test, goodness of fit. We will use it when we have a proposed distribution and we want to know if it's a good fit for the data. Or we could also say we want to know if our theoretical probabilities are correct. Okay, we have a total sample size n, and our sample items are classified into one of k groups. So in this case, we classified it into brand 1, brand 2, brand 3, brand 4. The assumptions is that all the expected cell counts are at least 5. Okay. Now, some books will give you different rules of thumbs about this. Some will say as long as they're all at least 5 and except for 1, or as long as not like more than 2 of them are less than 5 or something. We'll just go to make it easy as long as they're all at least 5. We can do the test. The null hypothesis is that all of our theoretical probabilities are correct, or you can also write it as the proposed distribution is a good fit for our data. The alternative is that at least one of the theoretical probabilities is incorrect, or the alternative is that the proposed distribution is not a good fit for our data. Notice we can use probabilities and proportions interchangeably. Now your expected count, anytime you want to find the expected count, it's just your total sample size times your theoretical probability for that group. Just what you're doing instinctively. Again, your test statistic is the observed minus expected squared divided by expected and add them all up. K minus 1 degrees of freedom, where again K is the number of groups you had. And your p-value is always the area to the right of your test statistic. So here's our first example. Usually the hardest part of these tests isn't like, can you do the test, it's just actually punching it all into your calculator. So example 2, using the information from example 1, conduct a hypothesis test to see if the new city has the same distribution of market shares as our old city. Remember that our sample size was 400. Okay. And I've already written down for you again your observed and expected counts. So let's start off by picking an alpha level. We don't have any specific rules, so let's just go with 105. And we've already written down our null alternative hypothesis once, but let's just practice it. So the null hypothesis could be that the theoretical probabilities are correct. With the theoretical probabilities being 20%, 35%, 30%, and 15%. And then my alternative would have to be that at least one of the theoretical probabilities is correct.
Or is it incorrect?
Sorry, yes, incorrect. That makes a lot more sense. So, no hypothesis, all the theoretical probabilities are correct. Alternative is at least one of them is incorrect. What else do we need that I've forgotten so far? So, the assumptions. Which we have to check the expected counts. Notice that we check the expected, not the observed counts. So the expected counts are at least 5. Well, all my expected counts go from 60 to 140, so I think we're good there. What always comes next in the hypothesis test? As well as the test statistic. So it's our chi-square test statistic, and it's the sum of the observed minus expected squared divided by expected. And we're just going to do that for each group. Okay, so for my first one, observed is 102. Minus the expected, which is 80, square it. And the part of my students usually mess up the most is they will now divide this by 102. Okay, which is incorrect because I'm supposed to divide by the expected value, which is 80. Okay, plus the next one, 121 minus 140, squared over 140, plus the next one of 120, minus 120 squared over 120. And the last one is 57 as my observed, minus my expected of 60, squared, make sure you divide it by the expected of 60. And put that into your calculator. And I'm saying my work from last year to know that that is 8.78. Save a little time. Can you see why I at least on like the test, I will always try and avoid giving you something that has more than like 4 or 5 cells because it will take you a long time to do this test. Okay. You'll also know sometimes on your homeworks I made you do some by hand and then some will say, okay, your test statistic is 16, just go with the rest of the test from there. Just again to save you a little bit of time. We also need degrees of freedom, which in this case are k minus 1. Remember, k is your number of groups. So in our case, how many groups did we have? 4. So we have 3 degrees of freedom. Actually, guys, I don't have the chi-square table on here, I don't think. Good. Let's just draw a picture though, for future reference. So my p-value. Here's my chi-square test statistic, and my chi-squared. And remember, the chi-squared is not symmetric. It has a long right tail. I should try and remember to draw it that way. Here's my test statistic of 8.78, and I was looking for the area to the right with 3 degrees of freedom, and my p-value is between 0.05 and 0.025. Now, compared to our level of significance, is that a big or a small p-value? Small p-value. Which means, of course, that we reject the null hypothesis. And what does that mean for us? So the alternative hypothesis is that at least one of our theoretical probabilities was incorrect. Now put that even more into the context of the problem, and what does that mean? The new city doesn't have the same distribution of market shares. And can you tell me how many of the market shares are going to be different? Just at least one. So we have strong evidence. Again, you need to put in that fact that we just have evidence. Remember, we haven't proven or anything, we just have evidence. Strong evidence that at least one of the market shares is different in the new city. Now, if we scroll back up to the first page, do you have your suspicions for which ones have different market shares? I suspect it's probably number 1 and 2, but as far as what we've confirmed statistically speaking, we just know that at least one is different. So any questions on that test now that we've done the full thing? Let's try the next example. So we think that the gender of a child follows a binomial distribution. We are interested in families with 4 children, and we think that the boys and girls are equally likely. Now we took a sample of 300 families, and we are going to be looking for how many are boys. Okay, so we have equally likely boys and girls. Okay, we'll assume that gender is independent because theoretically, we know biologically that it can change a little bit, but statistically speaking, it's close enough to say that they are independent, one child and the next child, their gender. Okay, and everything here is sounding like a binomial distribution. Okay, so independent, the probability is going to be 0.5 every time. We know that we're looking at 300 families. Okay. So we want to see if the gender of the child in 4 children families follows a binomial distribution with probability of a boy being equal to 0.5. Okay. So they looked at 300 families. The number of families that had 0 boys are 18, and there were 78 families that had 1 boy, 108 families that had 2 boys, 70 families with 3 boys, and 26 families with 4 boys. Now, to do our test, we were used to being given the theoretical probabilities. Well, how would you find the theoretical probabilities for this problem?
Take 0.5 and multiply it out the number of children.
And so like for 0 boys, what would be the theoretical probability? 0.5 to the 1?
So 4.
Oh, 0.5 to the 4? So theoretically it would be like 1 minus 0.5 to the 4. Right? Because, well, when you think about it, it's going to be symmetrical. Okay. So to get 0 boys, I have to have 4 girls, which is, the probability of a girl is 0.5, and we need 4 of them. Okay, which is, I'm going to put that in the calculator. 0.065. Okay, how would you do the 1 boy though?
You do this. Probability 1 boy
So we do need 1 boy
times the 3, or probability of getting a girl to the 3rd.
and we need 3 girls. But what else do we need? If you remember from the binomial probability section. Okay.
Well, the order doesn't matter, so you have all the different combinations, right?
We have all the different combinations because you can have a boy on the first one, or second child, or third child, or fourth child. So we need to take into effect how many different ways you can get 1 boy. So we do 4 children choose 1 boy. Which actually gives me 0.25. For 2 boys, we have to take into effect how many ways I can choose the 2 boys. And then I want the probability of a boy to the power of 2, because I want 2 boys. Probability of a girl to the power of 2 as well. Gives me 0.375. So to see how this one's just a little bit different, and they tell you the distribution, and you have to find the theoretical probabilities. Okay? And they could do this for a binomial distribution, or a uniform, or a normal, or a Poisson, or anything else like that, where they know how to calculate probabilities. They could say, does Poisson for this? And you'd have to go calculate the theoretical probabilities first. So the next one would be 4 choose 3, 0.5 to the power of 3, so we want 3 boys, and we want 1 girl, gives me 0.25. And the last one, okay, it would be 4 choose 4. Now what is 4 choose 4? If you put it on your calculator, 4 choose 4 is 1, which is why if you forget that, it's okay. Also on the first one it would have been 4 choose 0, which is 1, which is why we didn't have to put it in. Okay? Because there's only one way to make all of your 4 children be boys. Okay, so 4 choose 4, 0.5 to the power of 4, 0.5 to the power of 0, which gives me 0.0625. So those are theoretical probabilities. And then how do we find our expected counts? Expected counts are just the sample size times the theoretical probabilities. Okay. So my sample size is 300, so we have 300 times 0.0625, which gives me 18.75. Okay, my observed count was 18, my expected count was 18.75. Let's see, so for my next one, it's 300 times 0.25, gives me 75. 300 times 0.375 is 112.5. Notice here that we are getting fractions for our expected counts. Obviously, you can't have 18.75 families with 0 boys, but because it's the expected count, that's okay to get our fractions. 300 times the probability of 0.25 is again going to be 75, and 300 times 0.0625 will once again be 18.75. So we can look at these observed counts And the expected counts to compare, 18 and 18.75, that's really close, 78 and 75. 16 is pretty close, 108 and 112, we're only off by 4.5. 70 and 75 off by 5. 26 and 18.75, that's probably about the biggest difference, about 8. Okay, so how do you feel about this one, instinctively? Okay, I'm thinking it might be pretty good. If not, the p-value won't be super small, it might just come in on the threshold. But I'm not sure just by eyeballing it. We need to actually do the test. Now the assumption is that all of our expected values are at least 5. So all of our expected values are at least 5. Okay, smallest is 18, so yes. And we'll pick a significance level, 0.05. Okay, and how could we write the null alternative hypothesis? What could the null hypothesis be? I could say the proposed distribution fits my data. I could say all of these theoretical probabilities are correct, or I can be even more specific because of what they asked, because they want to know is the binomial distribution with p probability of equal to 0.5 appropriate for this data set. Okay, and so I could specifically say the null hypothesis is that the binomial distribution with, and how do you find a binomial distribution? You need the n, which is 4, and p, which is 0.5. So the binomial distribution with n equals 4 and p equals 0.5 fits our data. Okay, or that it is a good fit for our data. So again, we can just say the distribution fits our data. Theoretical probabilities are correct, or to put it into context even more, the binomial distribution with n equals 4 and p equals 0.5 fits our data. Okay. And the alternative would be that the binomial distribution with n equals 4 and p equals 0.5 does not fit our data. What comes next in our hypothesis test? Our test statistic. Okay, the formula for that again is observed minus expected squared divided by expected, and add them all up. So in this case, my observed is 18 minus the expected of 18.75 squared divided by 18.75 plus the next one of my observed of 78 minus the expected 75 squared divided by 75 plus, and then you'll notice I'll just do plus dot 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 at this point because it seems kind of silly to have to write them all out. If you can't put it in your calculator without writing them all out, then write them all out. But we'll just continue the pattern until we get to 26 minus the expected of 18.75 squared divided by 18.75. Okay. On the test, if you can do this, write at least 3 of them, enough to let me know that you knew what you were doing, I will accept that because that's what I've been doing up on the board. Okay. Anyone put that in their calculator already and get an answer for us? 3.467. else do we need? We need degrees of freedom, which is k minus 1. How many groups did we have? We have 5 groups. So 4 degrees of freedom. So for my p-value, we're at 3.467, and I have to look for the area to the right because it is a right tail test. Okay, so everyone look at your chi-square table that's in front of you. You want 4 degrees of freedom, and you're looking for 3.467, and where are you going to find it?
Greater than alpha equals 0.25.
Okay, it's greater than the 0.25 because it's off to the left side, so my p-value is bigger than 0.25. And we could use a computer to find that the exact p-value is 0.483, just in case you're curious at how much bigger. Okay, so how do you feel about that p-value?
That's been checked.
Okay, it's a big p-value, a very big p-value, and we will fail to reject the null hypothesis. So in this case, my null hypothesis is plausible. Okay, so it's plausible that the binomial distribution is a good fit for our data. Okay, but we'll just keep with the overall trend for this class as we always write our conclusion in terms of the alternative hypothesis. Because remember, we are always looking for evidence against the null hypothesis. We never look for evidence for the null hypothesis. Okay, so our conclusion is always in terms of the alternative. So we didn't find enough evidence to conclude that the binomial distribution with n equals 4 and p equals 0.5 is not a good fit for the data. So again, just not enough evidence to conclude that it's not a good fit, which means at this point we have no reason to not use the binomial distribution to describe our data. So 2 problems, how do you feel about that? Any questions? Then let's move on to the next section, which is the chi-square test of independence. So at one point we have looked at this table. Okay. Remember we were talking about your gender and your job, and we wanted to know if what your gender was affected your job, and we looked at conditional probabilities to see. Okay. And so what if we wanted to do a hypothesis test to answer the same question? Okay. So we want to know if your gender affects which job you get, so we're asking if gender and job are independent or dependent. Okay. Now independent means that gender and job do not affect each other. Dependent means gender and job do affect each other. Okay. Which one do you think might be our null hypothesis? What would be kind of like the status quo here? Okay, that they don't affect each other. Okay, it's kind of the whole innocent until proven guilty here. They'd be innocent if the gender and job don't affect each other. So the null hypothesis is that gender and job are independent. So don't affect. And of course, the opposite of independent is that they are dependent. Which means that they do affect each other. Okay, so what we're going to do is we follow the same ideas as the goodness of fit test. Okay, this is just kind of a derivative of the goodness of fit test. So our test statistic is chi-squared equals the sum of each observed count minus expected counts over, well, squared over expected counts. Okay, now our observed counts are easy. They're just on our table. Okay, these are our observed counts, the actual data. Okay, but how are we going to find the expected counts? Okay, so for our chi-squared goodness of fit test, we did sample size times each probability. Okay, so we need to find the theoretical probability for each cell in the table. Now, do you remember how to find the probability for independent events? Okay, so if A and B were independent events, then the probability of the intersection of A and B is the probability of A times the probability of B. Okay, so for example, our first cell is male and faculty. Okay. Notice it is the intersection of male and faculty. So if the null hypothesis is true, that would mean they are independent events. And so the probability of male and faculty is going to be equal to the probability of male times the probability of faculty. Now, looking up at this chart, okay, how would you find the probability of someone being male at this university? What is the probability of someone being male? There were a total of 200 males out of 300, so the total probability of them being male is 300, or 200 out of 300. Right? So this is 200 out of 300 times, now the probability of faculty, there are 120 faculty out of my total of 300, so we have 120 out of 300. Okay. So that's our probability. I'm just going to leave it like that for a minute. We'll see why. Okay. So this is how we find the probability of male and faculty. Now if we want the expected number of male faculty members, we need to multiply the total sample size by the theoretical probability of that cell. So our formula for the expected count is going to be so we wanted the expected number of male faculty members, so we have to multiply the total sample size by the theoretical probability, which was our 200 over 300 times 120 over 300, correct? Remember it? Okay, so our expected count, we're going to take our sample size, which was 300, and times it by our probability of 200 over 300 times 120 over 300. And what's going to happen to one of those 300s? Okay. We are going to have one of those 300s cancel out. So we have 200 times 120 over 300. And we can go back up and look at that table and see where did we pull these values. So this 200, that was a column total. So I was interested in the expected count for this cell. So 200 is the column total, 120 is the row total, and 300 is the overall total. So what we can do is we can make a formula that works every time, and it was just our column total times our row total divided by the overall total. Okay, so for our chi-square test for independence, every time you want to find an expected count for any cell, you just have to do column total times row total divided by the overall total. Now, this only works for the chi-square test of independence because we're working under the assumption that our cells were independent, and that was why we just did that multiplication for the probability. So we have our chi-square test of independence. We use this if we have a contingency table of two variables. Remember, our contingency table is just anytime you divide out like this and you have two variables, so gender and job. Notice that the setup of the table by default looks different than when we wanted to do our chi-square test of goodness of fit. So we want to know if the two variables affect each other, okay, if there's a relationship, or if they're independent or dependent, and we only have one sample from one population. Okay, so we just took one sample of people from the one university and then cross-classified them into gender and job type. Assumptions is again that all the expected cell counts are at least 5. The null hypothesis is that the two variables are independent or that there is no relationship between them. And alternative hypothesis is that they're dependent or that there is a relationship. Okay. Now your expected counts is row total times column total divided by the total sample size. And your test statistic, once again, is observed minus expected squared divided by expected and add them all up. Okay. But notice your degrees of freedom are different here. Okay, so that's the biggest difference between the two tests, that how you find the expected counts and how you find your degrees of freedom. So degrees of freedom are R minus 1 times C minus 1. And what do you think the R and C stand for? Row and column. So this is number of rows minus 1 times the number of columns minus 1. Okay, so when you describe this first table, how many rows would you say this table has? Okay, so we're kind of debating between 3 and 4. What do you guys think? 3. Okay, so as far as this goes, we don't count the totals. Just the actual data. And once again, our p-value is the area to the right. It's always to the right, so this is a right tail test. Any questions? So let's conduct a hypothesis test to see if your gender affects which job you get at the university. Okay. So notice I have a table for your observed counts and I have a table for your expected counts. So observed counts is just what we already started with. And we want to find the expected counts. So for male and faculty, remember it's just your row total times your column total divided by your grand total. Okay. So for, let's see. So for male and faculty, that's going to be 120 times 200 divided by 300. Anyone got an answer for me for that? 80? So my expected counts for this are 80. Let's try and do the male and salaried staff. Okay, the expected counts for males and salaried staff. So let's see, so salaried staff, the row total is 80 times the column total of 200 divided by my grand total of 300 gives me, let's see, 53.3. What if I wanted female and hourly staff for my expected count? What's my row total for hourly staff? Let's see, hourly staff gives me a row total of 100. The column total for females is 100 as well, and divide by the 300, which gives me 33.3. And you can just put the rest in your calculator. At this point, you should see the pattern. And we have 40, 26.7, and 66. Now, if I start adding these up, so go ahead and add up 80, 53.3, and 66.7. What do you get? 200. And add up the 40, 26.7, and 33.3. 100. Okay, notice that my total should match up with my observed count totals. That's not coincidence. Your totals will always be the same. That's a very good way to check your work. Accounting for rounding, sometimes you might be off a little on your rounding. Okay, so 80 and 40 should still put me back at 120. 53 and 26, and add 1 for the decimals, puts me back at 80. 66.7 and 33.3 puts me back at 100. And my grand total, no matter which way I add it, should be back to 300. And so just, again, make sure your totals match up with what they were before to check your work. Okay. So that was how you found your expected counts. Now let's actually start our hypothesis test. We'll check our assumptions. And assumptions is that all the expected counts are at least 5. Again, make sure you check your expected and not observed counts. So all of my expected counts, they're all at least 26, so we're good there. We also need to pick our level of significance alpha. Let's just mix things up. Let's go with 0.01. And then we need our null and alternative hypotheses. So the null hypothesis is that gender and job are independent, meaning they don't affect each other. And the alternative is gender and job are dependent. So they do affect each other. Next up is my test statistic. So it's the sum of each observed minus expected squared divided by expected. So it doesn't matter which order you add these cells up, of course, because addition is commutative. So I'm going to start with my observed of 110 minus the expected of 80 squared divided by 80. So I'm going to go ahead and write down what this should be on your own paper. You can see if it matches mine at the end. So we found that our test statistic is 66.3. Now let's find our degrees of freedom. So it's r minus 1 times C minus 1. Remember, R and C are the number of rows and columns, and we don't count the totals. So when you look at your table here, we have 1, 2, 3 rows and 2 columns. So 3 rows minus 1 times 2 columns minus 1 gives me 2 times 1, or 2. So we have 2 degrees of freedom. Now what does this kind of mean? So this degree of freedom, degrees of freedom for our chi-square test are actually kind of easy to understand. Okay? So you remember how we said that these totals have to match up. Okay? So if these totals have to match up, okay, then what if I erased a few of these numbers? And I only left 2 numbers. Okay? Could you tell me what all the rest of these cells had to be? Keeping in mind that the totals have to be the same as the observed totals. What would this cell have to be? 120 minus 80 is 40. Okay, and 80 minus 53.3 gives me 26.7. Why did I have to keep this 53.3? Why did I have to start with 2 numbers? Okay, because I want my degrees of freedom, but if this 53.3 was gone, how would you figure out either one of these 2 numbers? You couldn't. They could be any combination that add up to 120. So you have to start with at least 2 numbers. And because you only have to know 2 of these numbers, that's when you say it has 2 degrees of freedom. Okay, so that's just one of the places where degrees of freedom has a very direct application. It's kind of neat to see that. Okay, and also speaking of that, we could go back up to one of our goodness of fit tests. Okay, and so consider this example where we have 300 families. If we know that these expected counts have to add up to 300 families, if they have to add up to 300, how many of these numbers do you actually have to figure out before you could just start subtracting to find the other ones? 1 less. You would only have to know 4 of the numbers, and then you can subtract from 300 to get the last one. Okay, so on this one, my degrees of freedom should be 4, which is what the formula gives us. Okay, so kind of the degrees of freedom, this way you can think of it as how many cells you would actually have to figure out before you could just find the rest from the totals. But that's kind of a sidetrack. We have 2 degrees of freedom. Now we want to find our p-value. Let's see, my test statistic is 66.3. I'm looking for the area to the right tail. Chi-square tests are always to the right tail here. And I'm looking for the number 66.3. So you guys have a table in front of you. Look at 2 degrees of freedom and look for the number 66.3. Where is that going to be? Way off to the right, probably very, very close to 0 since we stop at 15.2, we have to go all the way to 66.3. But we can say for sure that it is less than 0.0005, probably very close to 0, I would guess. Anyone have a calculator that can tell us the exact p-value? I'm going to write this one down in the notes.
4.03 times 10 to the minus 15.
1.03 times 10 to the negative 15?
Oh, 4.03.
Oh, 4.03 times 10 to the negative 15. So, very small p-value, right? Okay, so small p-value. We can reject the null hypothesis. So, evidence that gender and job are dependent. Okay, so our official answer is gender and job are dependent. We have incredibly strong evidence that they are dependent. Okay, that's an incredibly small p-value. What could you say to your boss to put it even more in context if he doesn't remember what independent and dependent mean?
Gender would there's very strong evidence that gender affects the job.
Okay. Very strong evidence that gender affects the job. And I find it interesting that you said your gender affects your job. Okay. Statistically, we just say, okay, like one of them, at least one of them is affecting each other. They might both affect each other. But realistically in the situation, does what job you pick then determine your gender? No, right? So in this case, it makes sense to say that your gender affects your job type. So, extremely, not even just very strong, but extremely strong. Evidence that gender affects your job type. At this university. So sometimes it's pretty obvious which one is affecting the other one. Sometimes you might just know that somehow they're affecting each other. So any questions on this one? So this next problem asks, does subscribing to the Beacon News affect whether or not you subscribe to the Atlantic Journal? Okay. Now when you read this, it doesn't say do a chi-square test of independence, but when you see does something affect the other thing, that should make you think that you want to know if they are independent or dependent. Let's just go with our defaults. Alpha equals 0.05. Let's see, I need to check my assumptions, which is that all expected are at least 5. Okay. But I guess I'm going to jump in the gun because we haven't found our expected values yet. Okay. Notice here that I didn't give you two different tables because I found for myself when I'm doing this test that it makes it easier for me if I just write the expected values inside each cell, and then it makes it really easy to keep track of which numbers go together. Okay, so let's find all of the expected numbers first. So for Beacon News and Atlantic Journal, what do I need to type into my calculator? So Atlantic Journal and Beacon News, what numbers do I need to type in for that? So row total of 650 times my column total of 500 divided by my grand total of 1,000 gives me 325. Okay. So my expected count is 325. So I'm just going to go through my each expected count inside the cell that it goes to. So for not Beacon News and Atlantic Journal, I need 650 times 500 divided by 1,000 gives me 325 as well. Okay. Let's see, for my next one I have 350 times 500 divided by 1,000 gives me 175, and 350 times 500 divided by 1,000 gives me 175. Anything kind of interesting about this data set? Okay, the two columns are the same. Why are the two columns the same? Because these two column totals are the same. So that happens fairly often. You get a data set that looks like this, and that's okay, nothing changes. So are all of my expected values at least 5? Yes? And just remember, double check yourself, do your totals add up? So like 325 plus 325, that does give me 650, so we're good. What would my null hypothesis be? Okay, so Beacon News is independent of Atlantic Journal. So whether or not you subscribe to Beacon News is independent of whether or not you subscribe to the Atlantic Journal. So don't affect each other. And the alternative hypothesis is, of course, the Beacon News is dependent of Atlantic Journal, and vice versa, so they do affect each other. So our test statistic, we're going to find out. Once again, try this on your own so you can get the same answer. Remember, our formula is the sum of each observed minus expected squared divided by expected. So we should have gotten to 98.9. Any issues putting into your calculator? Then we also need degrees of freedom. So number of rows minus 1 times number of columns minus 1. Now how many rows and columns do I have? 2 and 2. So remember, we don't count the totals. So 2 minus 1 times 2 minus 1 gives me 1. So there's only 1 degree of freedom. So for my p-value, we have our test statistic of 98.9, and I'm looking for the area to be right with 1 degree of freedom. And so what is that area going to be? Looking at your table?
Really close to 0.
It is very close to 0. Specifically, all I can tell from the table is that it is less than 0.0005. But it is, my test statistic is so big that I'm willing to bet that that is very close to 0, like times 10 to the negative at least 15 or so. And so we would reject our null hypothesis, and they are dependent. So we could tell our boss something like, we have extremely strong evidence that subscriptions to Atlantic Journal and Beacon News affect each other. And when you think about it, that makes sense, right? If you're already subscribing to one journal, you're probably more likely to subscribe to another journal. Okay, at least I would assume so. Now in this situation, is it obvious which one is affecting the other variable? Okay. No, and in this situation, could it be plausible that they both affect each other? Okay. Yeah, so we'll just leave it as they affect each other. Any questions whatsoever? You technically now know enough that you can do your homework. We'll just practice some more problems, but you do know enough tonight to go home and do your homework for a chi-square test. Okay. Tomorrow what we'll do is we'll go over proportions quickly, but I won't actually give you a homework assignment or put it on the test. So we'll go over proportions for the first probably like half hour or so, and then you can bring questions from the review for the test. And the review is online, has been online for a little while.
You said proportions won't be on the test?
Yeah, so proportions will not be on the test. So let's go ahead and practice some more chi-squared problems. Okay. So notice here I did put in a mix of chi-squared problems just so you can get more used to trying to figure out which one is which. Okay. And what we'll do is I'll just on these ones tell you your chi-square test statistic to save us some time so we can just practice like what is our conclusions and how do we set it up. Okay, so our gender and voting preferences dependent. Which test do I want to use here? Okay, is it our goodness of fit or test of independence? Okay, so this is chi-square test of independence. So what I'm going to do here is we'll just skip to the, I'll just tell you that chi-squared equals 0.10. Okay, and then we'll do the rest of it. So we'll skip finding our expected counts, okay, just to save some time, just so we can practice conclusions, since I think we're good on the rest of the computations, right? Okay. So let's just skip our assumptions, assume that they're all at least 5. I can tell you that our expected counts are all at least 5. Which is alpha equals 0.05. What is your null hypothesis?
They're independent.
Okay, so gender and voting are independent. And the alternative is then gender and voting are dependent. So somehow they affect each other. So you need your test statistic, which we're just going to go with is 0.10, and then you need degrees of freedom. Okay, hardest part usually is remembering different degrees of freedom for independence, different degrees of freedom for test for goodness of fit. So for the test for independence, it's R minus 1 times C minus 1. Okay, so how many rows do I have? 2. And 3 columns gives me 2. So I need my p-value. My test statistic is 0.10, and I'm looking for the area to the right, and I have 2 degrees of freedom. So looking at your table, where is a 0.10 test statistic going to fall?
Far to the left.
Way to the left. So my p-value is bigger, probably much bigger than 0.25. Okay, because my test statistic is going to be way to the left. So my p-value is much bigger than 0.25, so that is a big p-value. No matter what level of significance I pick, that would be a big p-value, so we will accept, or we prefer to say fail to reject. I know your book says accept, but most people, it's much more generally accepted to say fail to reject. Okay, which means what?
There's not enough evidence to conclude the gender influences.
So not enough evidence to conclude that they're dependent, or like we said, to conclude that gender influences voting preferences. Okay, in this data set. Now we don't know enough information. This could have been one specific state, or it could have been a sample from the nation. Okay, but not enough evidence to conclude that gender influences voting preferences. Again, this is one situation where it's obvious which variable would affect the other variable. Okay. So any questions on this one? Okay, so, I guess I didn't put that problem. So let's just go to this one. Okay, so example 8. You just got a job at a radio station. In the past, the radio station has played music according to the following distribution. So here's our percentages, believing that it was the listener's preference. You think that the radio station's list of preferences is out of date and inaccurate. So you take a sample, a random sample of 500 listeners and ask them their preferences. Conduct a hypothesis test to see if the radio station should change their distribution of music preferences. Okay? And this is a situation where the station's probably not going to want to change their policy unless you have overwhelming evidence that it has changed. Because changing any policy is always time-consuming and expensive usually. Okay? So I can tell you that the expected counts are 20, 180, 55, 10, 90, and 145. Okay, to save us some time. And I guess I should have said, what test are we doing here first? Goodness of fit. And so we know for our chi-square test for goodness of fit, to find expected counts, you just take the total sample size of 500 and times it by the theoretical probabilities. Okay. Let's use alpha equals 0.05. Actually, wait. This is a good case to use 0.10. After all, it's not a drug or something that's really going to affect people. It is just music, so we might be okay with a higher significance level, and error is not going to mess us up that much. What would our null hypothesis be? There are multiple ways that you could phrase this. What is a good way to phrase this null hypothesis?
The radio plays what people like.
So the radio plays what people like. So distribution is correct. And the alternative would be that this distribution is incorrect, and specifically it would be, these probabilities would be incorrect for how many different genres? This one, so at least one genre's percentage is incorrect. Now, as one astute student pointed out once, if one is off, that by necessarily makes another one off as well, because they'll have to add up to 100%, but this is at least one genre's percentage is incorrect. Okay, our test statistic, again, would be observed minus expected squared divided by expected, and if you do the work, that ends up being 22.71. Degrees of freedom. What is the formula for degrees of freedom for this test? K minus 1. Okay. Where K is the number of groups. So how many groups did we have? How many different genres? Looks like 6. So 6 minus 1 is 5. So the p-value, we're looking for the area to the right of 22.71. Look at your table. What is this p-value? It looks like it is less than 0.0005. How much less than it? Just a little bit. Not very much on this one. Okay, and really it's just coincidence that all our p-values have been so small. So small p-value, we will reject the null hypothesis. Okay, and we have extremely strong evidence that the old distribution doesn't match current taste. Okay, so we've done 3 problems of each. Any questions?